Hello, good morning, everyone. Welcome to lecture 36. We will do some solved problems. So we have seen some theory already. So let us see theory on like covariance, correlations, and so on. So let us do some practice with some examples. So consider this example here, where we choose a point xy uniformly at random from the following disk. So the disk is the following. So yeah, so it's a center at 0 and radius 1. So the question is, so the joint PDF is given to us for this. So this is inside the disk, it takes constant value and it's 0 otherwise. And the question is, are x and y uncorrelated? Okay, so are x and y uncorrelated? Okay, so this is like this. Okay, and this disk values are here. Okay, so this is the region x square plus y square is less than equal to 1. And yeah, so we are picking a point at random, right? So let us say some point xi, yi is chosen at random from here. And the probability of that point, right, being in the disk is like given by C. Random variables, uncorrelated. Okay, so are these uncorrelated? That's the question. So let us see how we can try to do this. So uncorrelated would mean that the covariance of x and y must be 0. Okay, so this will mean that in other words, this would mean like covariance of x y is equal to 0. Okay, so this is what we are supposed to solve. Okay, to find and yeah, so to get to covariance, okay, so what was the formula for the covariance? So covariance was covariance of xy is expectation of xy minus expectation of x, expectation of y. Okay, so this is the formula of covariance. So what we really need are the expectations. Okay, so we need to compute these expectations. And are x and y given individually? No. Okay, so x and y are not given individually. The joint is given to us. Okay, so we need to figure out how to compute expectation of x and expectation of y. Okay, and yeah, so and also obviously expectation of the product, right? So this is the product of xy, right? So this is also we are not given directly, right? So we are supposed to do this. Okay. So one thing we notice is like from the previous example that we did on this. So there was one example on this before. So what we have already is the following. Earlier, we found that x and y are and we also found out that xy is x given y is a uniform. Okay, so this is uniform minus square root of 1 minus y square and then square root of 1 minus y square. You can verify this. Okay, if you want, you can go ahead and prove this also. So this is something we know. So what we know is the conditional, okay, but not explicitly about x and y. Okay, so remember when we are given conditional and we are supposed to find expectation of we are supposed to find expectations, right? So in that case, the thing that we use is the law of iterated expectation, right? So we can try that. Okay. So what we want is so we want to find the covariance of xy, which is expectation of xy and then minus expectation of x, expectation of y. Okay, so this is something we recall. And now to compute the expectation of x, let us say I'm going to use the conditional and apply the law of iterated expectation. So expectation of x is expectation of x given y. Okay, and this is using LOIE, and expectation of x given y. So x given y is a uniform. So this will be 0. Okay, so this will be 0. And so this will be expectation of 0 will be 0. Okay, so this is because since x given y is uniform. Okay, so and we also want to find the expectation of xy, right? So expectation of xy, again we will use the law of iterated expectation trick here, and in this case we want xy, right? So we will write that. So expectation of xy and given y. Okay, so in this case y is given. Okay, so y is given, so y can be treated as a constant, so it will come out of the expectation. So y expectation of x, and this will be, so again going to be 0, right? So and then whole thing will be 0 again. Okay, so this implies that covariance of xy, which is expectation of xy minus expectation of x, expectation of y. So this is 0 and expectation of x is 0, so we don't care about y, even though we did not find out about y. So this turned out to be 0. Okay, so in these calculations, what you notice is like you compute only one of these, and if it turns out to be 0, you don't care about the other one. Okay, you don't care because overall this will be 0, so your focus should go on xy as the next step. So this is what we did. Once we found out x is 0, we immediately went there and found xy. Okay, so covariance 0, this implies that the correlation xy is 0. Is correlation xy 0, right? So this is, in other words, xy is uncorrelated. Okay, so it's uncorrelated. So this is the proof that we had to do. Okay, so that was the question. Okay, now we will go to a topic that's bivariate normal distribution. Okay, so let us see what that means. But before that, I will show some motivating example of how we can obtain bivariate normal distribution. Okay, I have not defined this yet, but let us start with some example and see what happens. So let us consider two random variables, x and w here. So x is a normally distributed, obviously, standard normal with mean 0 and variance 1, and w is Bernoulli with probability half, be two independent random variable. And let the random variable y be a function of x and w as follows. So let us define a function y which is a function of x and w, where x is normal and w is Bernoulli, and it's defined in this way. Okay. Since the second one is Bernoulli, it has two possibilities, right? So it's 0 or 1. And for those values, we are defined x. Okay. So I mean, for those values of w, we have defined y values, okay, which is in terms of x. So the question is find the PDF of the random variable, and then we are asking what would be the PDF of y. Okay, y which is a function of x and w. So one thing to notice here is that if X is a normal distribution, the negative of X also follows a normal distribution. So that's a easy thing to establish. Okay, so because of the symmetry of the normal distribution, minus X will also be a standard normal. Okay, so N0, 1. So that's the first observation we make. And then, yeah, so we are supposed to find the PDF. So what should be done, right? So in this case, I see that the variable W is Bernoulli, and perhaps I can find I can use like total probability because I can condition on W. Okay, I can condition on W. So the first term will be conditioned on W equal to 0. Second term will be conditioned on W equals to 1. Okay, so that could be done here. Okay, and let's see and apply the conditional probability. In fact, I may go ahead and do the CDF of this, and from the CDF, I will see if I can get the PDF. Okay, so in the CDF, I would like to use the total probability. Okay, so that will be my plan. So let us see what we do with this, because things are given in terms of one is a very good option here. Okay, so let us see what can be done here. So if so due to symmetry, the first point is like due to symmetry. So due to symmetry, so due to symmetry of the normal distribution about 0, minus X is also a normal distribution 0, 1. Okay, so that's the first thing. And then I would like to go ahead and apply the CDF and see what CDF looks like. So probability that Y less than equal to Y, and this is, I will now apply the total probability. So probability that Y less than equal to Y given W equal to 0, and then probability of W equal to 0 plus probability that Y is less than equal to Y given that W equal to 1 now, and probability that W is equal to 1. Okay, so probability that W equal to 0, so it's a binomial with probability half, so that will be half only. So this will be half of probability that Y less than equal to Y, W equal to 0, plus half probability that Y less than equal to Y and W equal to 1, given that W equal to 1. Okay, and X and W, are they independent? Yes, they are independent, right? So these two things made me use the total. So even independence is there, so the conditionals will get simplified. So half, and so there is no dependence on W, so this will go away and this will go away. So this is just probability that Y less than equal to Y plus half probability that Y less than equal to Y. Okay, well, this is just probability that Y less than equal to Y1, probability, but yeah, so it's probability that Y less than equal to Y. Okay, and what else? So is it yeah, so but I think where is the X in picture, right? Because I have to derive things in terms of X, but so I should start substituting Y X actually, right? So I have done a mistake here. Let me correct this, because yeah, let me I have to fall back on X because that is the given thing, right? So W equal to 0, I will be having Y equal to X, right? So half probability that X less than equal to Y and because x is known to me, so that's why I will do that. And for w equal to 1, y is like minus x less than equal to y. Right. Okay. Now you see x minus x is also normal by symmetry, right? So this will be phi of y. This is like standard normal, right? So remember standard normal, the CDF values are given by this phi function, right? Which are tabulated, right? In general, we don't know the closed form, but the tabulated values are there. And minus x is also standard normal. So it will also be, it follows the exactly n01. Okay, so this will also be phi y again. All this is coming the fact that so this is again phi y. Okay, so this is like phi y. Okay, total after adding. Okay, so this is what we have. So what do we observe from here is that the CDF is exactly the CDF of standard normal, right? So this is a CDF of standard normal exactly, right? So Fy with y is given by phi y. This is exactly because CDF values are given by the standard normal, right? Okay, so so the question was find the PDF of y, right? So from here we can already claim that this implies that y is standard normal. So the PDF will be the same as the PDF of the standard normal, right? So 1 by square root of 2 pi e to the x square by 2 and so on, right? So yeah, so we can stop here. Okay, so that's the answer to this question. So yeah, so our motivation to bivariate normal, we've seen one example. So now let us define what is bivariate normal. Two random variables x and y are called bivariate normal or jointly normal if ax plus by has a normal distribution for all a comma b in R. Okay, so two random variables will be defined to be bivariate normal if their linear combination is also a normal distribution. Okay, if the linear combination is also a normal distribution for all a and b. In general, it will not be the case. Okay, so in general, it will not be the case because there are counter examples where we can say that the linear combination may not be normal. Okay, so but if it happens that ax plus by behaves like a normal distribution, then we define x and y to be bivariate normal or jointly normal. So so if a and b are 0, obviously this is a zero random variable, right? So for 0 random variable, it also can be seen as a normal distribution with mean and variance 0. Okay, with mean and variance 0, right? And if x and y are bivariate normal, then by letting a equals to 1 and b equal to 0, x must be normal. So these are the properties of bivariate normal. And so if they are known to be bivariate normal, then it must be that if a is 0, then if a is 1 and b is 0, then x must be normal. And same thing we can say the other way. If a is 0 and b is 1, then y must be normal. If x follows a normal distribution with mean mu x and variance sigma x square, and y follows a normal distribution, it's not equal here. So normal distribution with mu y and sigma square or sigma y squared, and they are independent, then they are jointly normal. Okay, so if x follows the normal distribution, y follows the normal distribution, and moreover they are independent, then they will be jointly normal. In other words, like if I take a linear combination of this ax plus by, then if I take a linear combination of ax plus by, then it will be a normal distribution as well. Okay, so if it indeed is the case that they are jointly normal, then how do they look like? They look like this. So x plus y is a normal with mean just the sum of the mean of the two random variables, and then the variance is a little bit complicated. So it's like sigma x square plus sigma y square. So this is a variance of x plus variance of y plus some mixed term here. Okay, so 2 times the correlation of xy and then multiplied by the sigma x and sigma y. Okay, standard deviation. So there is a way to know, like if someone tells you already that x is normal with mean and variance, y is normal with mean and variance, then what could be what could be the distribution of the sum. Okay, what could be the distribution of the sum? Can be just adding the. So this is the fact that we know. So the question is like, can we provide a simple way to generate jointly normal random variables? Okay, so can we provide a simple way to generate jointly normal random variable? So given two random variables, like can we do something to create jointly normal, right? Right now we are saying when they are jointly normal, what are the things we expect? Okay, what are the things we expect? Like everywhere we are saying, okay, if they are jointly normal, then x plus y will look like this. If they are jointly normal or bivariate normal, both are the same word, right? Bivariate normal, jointly normal, same thing. So if bivariate normal, then if we do this, if a is 0 and b is 1, if we take a linear combination and then we take a equal to b equal to 1, then, well, what it means is like individually y must be normal, x must be normal, and so on. Okay, so this is when it's already bivariate normal, then we know what to expect. Now the question is like how we can generate a jointly normal random variables. Okay? So can we generate a way? Is there a way to generate jointly normal? Okay, let us go through this, right? So let us see if there is a way. So as in the previous case, we have seen that we start from standard normal. Okay, and then we move to the general case mu x and sigma x square. So standard normal to just normal. Okay, so this is a more general normal case. We know that they are related, right? If I'm given this, then I know how to define. If x follows this, then I know how to do a proper scaling of x. Okay, if I recall, then x minus mu x by sigma x, right? Something like this you define, right? Then with this scaling, then Z behaves like a normal, standard normal. Okay, so from non-normal, or we should not say abnormal, but it's like non-normal case or the just normal, we get standard normal by doing this kind of a scaling, right? So one can always prove that this will behave like a standard normal. Because expectation is very simply 0 because linearity, and then variance also you can check that with this it will become 1. So that was the case for the single variable case. Now we are talking about jointly normal and so the idea would be, approach would be similar. Once you start with standard bivariate normal distribution, and once you know how to work with them, you can actually also define the general cases. Okay, you can also define a general case. So from here you can also solve for x, right? So x will be sigma x z plus mu x. So if I'm given a standard normal, then I know how to go to a normal with expectation mu x and variance sigma x square. Okay, so both way we can go. So this is our same plan is like, now we first study the standard normal and then we will see how to go to the bivariate normal with appropriate scaling. Okay, so let us work with some example here. So let Z1 and Z2 be two independent a normal random variable, we define, okay, so here the scaling is a little bit different here, okay, obviously, because we are dealing with two random variable now. So Z1 is given to me, Z2 is given to be independent and normal, standard normal. So X I defined it to be like this, and Y I define it to be something like this. Okay, so it's a little bit more, but let's see what effect it has, right? So where rho is a real number between -1 and 1. So that's also like given to us. Now the question is X and Y, with this definition of X and Y, can we say that X and Y is bivariate normal? Okay, so can we say that? Okay, in other words, what do we want to prove? So what was the definition of bivariate normal? Bivariate normal is when the linear combination has a normal distribution, right? So this is what we are supposed to prove. So we are supposed to prove that any linear combination of this X and Y, if it turns out to be a normal distribution, then I will claim that X comma Y is a bivariate normal. What is the joint PDF of X and Y? Okay, so that's another question. What is the joint PDF? Obviously they are like related, and then find the correlation of X and Y. The way I have defined X and Y in this form. So what could be the correlation of X and Y, right? So let us see with this example or fact or whatever you can say. Okay, so this gives us, this perhaps will give us a method of how to obtain bivariate normal, just starting with a standard normal. Okay, standard normal, like many tools are there. Okay, like all the libraries will give you standard normal. All the tools are there to play with standard normal, and then with your own for your own normal variable, you can just fall back on standard normal. Okay, so let us see. From standard normal, we define our own normal. Okay, and then I mean we don't know yet. Okay, whether of course X is Z1, so X will be by default normal, but we don't know about Y yet. Okay, is this going to be normal also, or so on? Okay, but what we really want to see is, are they at least bivariate normal, right? So let us see, is this the case? So first we note that Z1 and Z2 are normal and independent. Okay, so if they are normal and independent, since they are independent, the joint PDF, we know joint PDF is the product of the individual PDF. Okay, so that we can immediately write down, and so note that Z1 and Z2. Okay, so these are Z1 and Z2, two random variables, are normal and independent. Okay, so and independent. So in that case, F Z1 Z2 is F Z1 F Z2 because of the independence. The joint PDF is product of the individual PDF. So in this case, if we write down, so what was that? 1 by square root of 2 pi e to the minus Z1 square by 2, and similarly 1 by square root of 2 pi e to the minus Z2 square by 2 is Z. Okay, so 1 by square root of 2 pi, 1 by square root of 2 pi is 1 by 2 pi, and e to the minus half can be taken common, and this is sum of Z1 square plus Z2 square. Okay, so what we see is like this is so this is like this behaves like a jointly normal, because that it is the form of the normal again, right? So it behaves like a jointly normal, and so we can leave it here. Okay, so that's now we go back to our question. Okay, is X and Y bivariate? So we have to take the linear combination of X and Y, AX plus BY, right? So let us see the answer to that. So we need to show that. So need to show that AX plus BY is normal for all A, B in R. So this is what we are supposed to show. So what do we have? AX plus BY is A Z1 plus B, and then what was the rho Z1 plus square root of 1 minus rho square Z2. Okay, so this is rho Z1 plus 1 minus rho squared Z2. Okay, now what do we have here? So this is like A Z1. Okay, so here I can take something common. So A plus B rho Z1 plus okay, so B and 1 minus rho square Z2. Okay, so this is a constant and this is a constant. So this is a linear combination of two. It turns out that this is a linear combination of two standard normal. So linear combination of two standard normal is normal. Okay, so that's a fact we can prove easily. Okay, so it's linear combination of two normal standard normal is normal. Okay, so it is like which is a linear combination of Z1 and Z2. Okay, this implies that it is normal. Okay, so linear combination of two standard normal is normal. So that's the part that is okay. So it is bivariate normal because the linear combination turned out to be normal, because it turned out to be just a linear combination of standard normal. Standard normals are saying standard normal is not necessarily standard normal, but they are normal. Okay, so this is what we have. And what is the joint PDF of X and Y? Okay, so to do the joint PDF, we need to invoke the method of the function of method of transformation here, because it involves the function that goes from like Z1 Z2 Z1 Z2, and then it outputs XY. Okay, so and it's, yeah, so we are supposed to find the joint PDF of XY, so we will invoke the method of transform. So in the method of transform, what we need is the inverse function, right? So what we need is the inverse of F. Okay, so in there it was G, I guess. So what we need is the inverse of G. So in other words, we need to solve for Z1 and Z2 here. It's a linear, it's kind of a linear relationship, so it's easy to solve. And once we have that, then we will use the method of transform formula. Okay, so let us go with this idea. So for B, using the method of transformation, okay, method of transformation to find the joint PDF of X and Y. Okay, so first we need to find inverse. So the inverse function is, so inverse we need to find. So Z1 is simply X, and this we can take it as, define this as H1 XY, and okay, so Z1 is X, so it will be minus, so if I solve for Z2, then it will be Y minus rho X, okay, and then divided by this, right? So rho minus rho x divided by 1 minus rho square, and then plus y by 1 minus rho square. Okay. So Z2 will be minus rho by 1 minus rho square x plus y by 1 minus rho squared. And this we define it to be H2 xy. Okay, so now recall the method of transform formula. So what was that? F xy z1 z2 is f z1 z2 h1 xy and h2 xy. Okay, the joint PDF we have computed before. So f z1 z2 we know. Okay, so this is the form of f z1 z2. So 1 by 2 pi e to the minus. So this is something we know. H1 we know, H2 we know, and then additionally we need the Jacobian. Okay, so our focus is now here because all other things are known. So the Jacobian, if you remember, is determinant of del H1 by del x, del H1 by del y, and del H2 by del x, and del H2 del y. And del and del H2 by del x is minus rho by square root of 1 minus rho square. So minus rho by square root of 1 minus rho squared, and then for y it's just 1 by 1 minus rho square. This is 1 by 1 minus rho squared. Or okay, so we take a determinant of this. So this will be just 1 by square root of 1 minus rho squared. Okay, so from here we can now use the star. So this implies fx y xy is yeah, so 1 by 2 pi, okay, e to the minus half. So 1 by 2 pi exp minus half, and then inside we have z1 square, right? So z1 square is just x square plus yeah, z1 square is x square, and then plus z2 square, right? Yeah, so we have to put h1 there. So h1 is x1 square, and now we have to put h2 square. Yes, so now the next step is h2 square. So h2 square will be yeah, so this term here. Okay, so 1 by h2 squared is there, right? So this square will, so 1 by 1 minus rho square will come out, and then minus rho x plus y, right? So this will be plus 1 by 1 minus rho y squared. Okay, and then also we had the Jacobian, right? So Jacobian is 1 by square root of 1 minus rho squared. Okay, so this is what we have. So yeah, so we can simplify a little bit and put this 1 minus 1 by rho here because that is outside. And what else we can do? Yeah, let us simplify this further. So fxy xy after simplification will be 1 by 2 pi and 1 by 1 minus rho square. We keep it here, and then we had the exponential term. So exponential term is, I take this common minus, so 1 minus 1 by 1 minus rho square, let us say I take common. So minus 1 by, but then there is a 2 also, right? So I can take 2 also common. So 2 1 minus rho squared, and then what is left here is Okay, so what is left? So inside what will happen, right? So inside, what would happen is I will have 1 minus rho square x square. So I will have x square minus rho square x square, and there is a plus rho square x square term here, so that will get cancelled. So okay, so I will be left with just x square term, because minus 1 I've already taken common. So what will be left is x square term, and then minus. Okay, so this is like minus 2 rho xy term is there. Okay, so minus 2 rho xy term, minus 2 rho xy term is there, and then plus y square is there, and then I will close it. Okay, so you can verify that this will be the case. Okay, because here it will be like let us say x square, but then there is a minus 1 here, so there will be the minus x square. I see minus x square if I multiply this minus back, and then inside I had 2 rho square, 2 rho xy, right? So inside I have 2 rho xy. So I have 2 rho xy, and then minus plus will happen. So here also minus plus would happen, and then plus y square is there. So plus y square is there, and then because of the minus term above, okay, so if I multiply throughout, it will again become minus and so on. So this is correct. Okay, so the reason for spending time on this is like this will be used in the definition. Okay, so these are the correlations, right? Rho and yeah, so this is the joint PDF, and when some correlation is given to us, remember, if the correlation is going to be 0, fall back on. So if correlation is 0, then you know that it will behave like the what PDF of the independent standard normal, right? So two independent standard normal look like this, right? 1 by 2 pi e to the minus half z1 square plus z2 square, right? So this will be 1 by 2 pi, okay, and this is 0. So minus x square plus y square by half. Okay, so that's exactly like, so if that is the case, then we immediately know that fxy is 1 by 2 pi e to the minus half x square plus y square. So behaves like, not behaves like, this is like, right? So this is PDF of jointly normal standard. So this is the PDF of joint PDF of standard normal. Okay, so that's what we saw when we were working with Z. We were given two normal and independent, and that's what it came out to be. So this is being produced here the moment rho is equal to 0. So rho is equal to 0. So obviously from here also it's very clear, right? So rho being 0, obviously it becomes Z2, right? So X is becoming Z1 and Y is becoming Z2. So there is no surprise that if rho is 0, then they will be just normal, okay, two normal, and then so we are doing it in a reverse way, right? Now this is what we are going to use it in defining in general case, right? So let us see what I'm going to define now. So two random variables x and y are said to have standard bivariate normal distribution with correlation coefficient rho if their joint PDF is given by this. So this is exactly what we derived. Okay, so we define a standard bivariate normal distribution, but the correlation is not 0. Okay, so if the correlation is not 0, in that case we come up with this definition. Okay, where so there is nothing here, I guess. So That's the definition, okay? That's the definition of the standard bivariate normal distribution with correlation coefficient rho. So when the correlation coefficient is not 0, then the standard bivariate normal distribution that we are going to get is this, okay? So if they are, so what was the other case, right? So other case was when they were independent, right? So if X and Y were independent, then what was the covariance, right? So covariance of XY was expectation of XY minus expectation of X, expectation of Y. So if XY independent, then this will be expectation of XY is expectation of X and then expectation of Y, right? Goes to 0, right? So covariance becomes 0, okay? So then the correlation will be 0, right? So correlation will be 0. Then we fall back on on this case, right? Correlation is 0, we get a simplified version of the joint PDF. If the correlation is not 0, then you are going to get this, okay? So that's a slightly general case than the previous case, right? In other words, they may not be independent, right? And then we can still define some joint bivariate, standard normal bivariate distribution. Okay. So I think there is some mistake here. Okay. So if yeah, so here rho is defined to be between -1 and 1. Okay. So if rho is indeed 0, then we call them. Okay, 1 second. Why I'm saying normal 2 times here. Okay, so then we call X and Y to be standard normal bivariate normal distribution. Yeah, okay. Here, yeah, so the terms are not very well. I have a typo here. Okay, so it will be if rho is 0, then the term that we use is that it's standard bivariate normal, and if the correlation is not 0, then we call it okay, I'm a bit, let's see. So I'm a bit, let me see, but I have a typo here. Yeah, okay, sorry, I'm one second. Yeah, so I'm a bit, yeah, so if the rho, we just don't say this additional term, okay? We just don't give additional term. So there is a little bit of confusion here in the way we are saying things. I mean, one way to say is like standard bivariate normal distribution with correlation coefficient rho, right? And here we don't say anything about the correlation, so we just stop here. So standard bivariate anything about correlation coefficient here. Okay, so that's the thing we have to remember. If the rho is equal to 0, then we just say that they follow standard bivariate normal distribution, but we are not saying anything about the correlation here. Okay, so that's there is a very subtle thing here. I was just about to text. Okay, another way to say is like with. So that's why I was also confused, right? So with correlation 0, right? So you can append this additional term, and yeah, that's fine. Because if correlation equal to 0, we know what it means, right? So it's a subtle thing, like, so if this is when the correlation is there, in other words, like correlation is non-zero, and if the correlation is given to be 0, we don't even indicate that in words. We just say it's standard bivariate normal. And if the correlation is non-zero, then we say standard bivariate normal with whatever value the correlation has. Okay, sorry about the thing. Okay, but this should not be confusing at all, because from the form we will always identify whether the row is 0 or not. If it boils down to form minus half x squared plus y squared, we already know that correlation is 0, right? Okay, so and from this standard normal, we can now define the bivariate normal, right? Right. So far we were talking about standard normal and then bivariate distributions. Now we are talking about from standard, how can we go to just normal? Okay, just like previously we went from normal 0, 1 to normal mu x and sigma x square. Now we are going from normal, but now in the case bivariate now. So now we go from bivariate normal to bivariate standard normal to bivariate normal. Okay, there are too many things going on now, so these are big words. So but the way it is defined is exactly this. Okay, so again, like this is the definition, just take it like that. Okay, so this is how the bivariate um, the joint PDF of a bivariate normal distribution is defined to be like this. Okay, so from here you can already see that if I would have scaled my variables, right? So if I would scale z to be x minus mu x by sigma x, so this my in the form in z form, if you see like see that, then it will boil down to z1 square plus z2 square minus 2 rho z1 z2 and so on. Okay, so it's a matter of scaling, because now we are given mu x mu y and so on. So we can write those variables in terms of the standard normal, and then just substitute that. Okay, so and then just substitute that in. So we know that if x is mu x sigma x square, then I can express x as a function of the. So from here I can express x as sigma x z plus mu x. Similarly, if y is given to be mu y and sigma y squared, and then I can express y as sigma y. So let us say this is z1 and this is z2 plus mu y, right? So I can use this. I can fall back on the standard normal, and then I solve for those. So if I solve for those, then I get z1 to be this, and z2 to be y minus mu y by sigma y. Now this is z1 and z2 are standard normal, right? So z1, z2 are standard normal. So now for the standard normal, I can plug in the formula that we derived here. Okay, so a standard normal bivariate we know, and then we change back to x after substituting those. Again, substitute back, go back to x, and if you do all these calculations, you will get to this. Okay, so that was the reason why we started with standard normal bivariate PDF, and then now we are extending this to any to the general just normal distribution. So okay, and yeah, there are assumptions on like sigma obviously should be 0. normal. What I'm trying to say is like it's enough to memorize only this guy, and the normal you can just find out by using the proper scaling. Okay, so how do you now create a jointly normal distribution, right? So if you want two jointly normal random variable x and y, where x is known to you and y is known to you and rho is known to you, then we start with two independent standard normal random variable, like, okay, and then you can define them to be like this, okay, and follow the above procedure and solve for Z1 and Z2 and apply the method of transformation and so on. So this is one way. This is one way where I can do this kind of scaling. Okay, so I think what I described you here was not correct, right? Yeah, I mean, just this will not work actually. Okay, I want to recorrect myself. If you want to get jointly normal, we have to define it in exactly this way actually. Okay, so there is something more needed here. Okay, then just to get to the joint bivariate. Okay, so this is not correct. Okay, so what I said here will not lead to this. Okay, so because since this is joint, yeah, we need to take care of the correlations and so on, right? So we need to define y to be like this. X is like as before, you do in for the single variable case, but then here we need to adjust a little bit more. And with this choice, okay, then and then solving Z1 and Z2 we have to do, right? So if we solve Z1 and Z2 and then we have to apply method of transform, and all this we do, and then we get to this. So apply method of transform, then we will get the PDF like this. So this is something you can verify. I claim that this will be the case. So solve for Z1 and Z2, okay, and then apply the method of transform and so on. Okay, so I believe I can stop here. Okay, so this is more or less the end of the bivariate normal distribution. Is very important distribution. So we are working with this. Yeah, in the next class we have to move to the multiple random variables, probability bounds, and then statistical inference. Okay, so that will be the remaining topic. Okay, so let us stop here and yeah, see you next time. Okay, bye.